Good evening, everyone, and welcome. Thank you so much for tuning in tonight. My name is Kate Bruns, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I am so pleased to welcome you to this evening's event with Steven Weinberg, discussing his classic book, The First 3 Minutes, A Modern View of the Origin of the Universe, in conversation tonight with Andrew Strominger and moderated by Melissa Franklin. Tonight's lecture is a part of our Harvard Science Book Talk series, which brings the authors of recently published science-related literature to our Cambridge community and now very, very far beyond. Coming up on April 21st, we're going to be hosting science journalist Annalee Newitz discussing their latest book, 4 Lost Cities, A Secret History of the Urban Age. To learn more about the Science Book Talks, you can visit the webpage harvard.com/science, or sign up for the bookstore's email newsletter at harvard.com. We also have a YouTube page where you can view previous talks you might have missed. And I'm going to be posting links in the Zoom chat in just a few minutes. This evening's event will conclude with some time for your questions. If you would like to ask our speakers something, please go to the Q&A chat at the bottom of the screen where you can submit a question. We'll get through as many as time allows for. I would also like to say a tremendous thank you for your patronage during these strange virtual times. Your support makes this author series possible and ensures the future of a landmark independent bookstore. So thank you to our partners at Harvard University, and thanks to all of you for tuning in and showing up for our authors, indie bookselling, and especially for science. And finally, as you might have experienced in virtual gatherings, technical issues can arise, and if they do, I'm going to do my best to resolve them quickly. So thank you for your patience and your understanding. And now I am honored to introduce tonight's speakers. A world-renowned theoretical physicist, Steven Weinberg is professor of physics and astronomy at the University of Texas at Austin. His groundbreaking research on elementary particle physics and cosmology that gave rise to the electroweak standard model earned him the Nobel Prize in Physics, the National Medal of Science, and numerous other awards. His work effectively shaped the direction for high-energy particle physics research and inspired the development of CERN in Geneva, Switzerland. He's published over 300 scientific articles, 6 treatises, and several books, including To Explain the World, The Discovery of Modern Science, and Dreams of a Final Theory, The Scientist's Search for the Ultimate Laws of Nature. He's joined in conversation tonight by Gwyll E. York Professor of Physics at Harvard, Andrew Strominger, who's likewise been widely awarded for his groundbreaking research, specializing in classical and quantum gravity, quantum field theory, and string theory, and earning him the prestigious 2017 Breakthrough Prize. He's also a founding member of the Black Hole Initiative, the first worldwide center to focus on the study of black holes. And moderating their conversation tonight is eminent particle physicist and Mallinckrodt Professor of Physics at Harvard, Melissa Franklin. Tonight, they'll be discussing Dr. Weinberg's 1977 popular science classic, The First 3 Minutes, which details the standard model of the origin of the universe. It's been hailed by the New York Review of Books as science writing at its best. We're so honored to host them for this conversation tonight. So without further ado, Dr. Franklin, Dr. Strominger, and Dr. Weinstein, the digital podium is now yours.
Here we are.
Thanks, Kate. So tonight we're going to be discussing 2 books. The First 3 Minutes, which is a classic, and also a much more recent book, which is a collection of essays, and that's called Third Thoughts. So I wanted to start with The First 3 Minutes. That was a book. It started as a public lecture you gave at the Harvard Science Center. And this was at a time when 1977 or 1975, something like that, when the world of particle physics was wild with new things happening. We had just discovered the charmed quark, the tau lepton, and you were not an expert in cosmology, and yet you gave this talk, this public lecture, and then it was so good that people convinced you to write a book about it. I'm kind of interested in what made you write the book.
Oh, as you say, only a small fraction of my work is in cosmology, but I had written a treatise about 5 years earlier, a serious graduate level book on general relativity called Gravitation and Cosmology. And I had learned how cosmology had recently evolved into what I think these days philosophers call normal science. That is, it's a scientific discipline like chemistry or geology where there are well-established standards for judging things. There are experiments that everyone are waiting to be performed. It's no longer what it was when I first started learning physics, a kind of mystical, semi-dogmatic field. I think the thing that turned cosmology around and that turned me around in the sense that I became fascinated by it was the discovery in 1965 of a microwave radiation background filling the universe. And it was, I wrote the book in 72 to understand that. And then when I was asked by George Field, professor of astronomy at Harvard, to give the talk at the Undergraduate Science Center, it all just came out of that earlier 1972 book. Actually, I don't know if it was how wonderful my talk was that instigated the first 3 minutes. I made a wisecrack during my talk. I said, I described the evolution of the universe starting with a time when it's filled with elementary particles, no atoms, no atomic nuclei even. It was too hot for atomic nuclei to hold together. This is like the first second of the Big Bang. And then the universe expanded and cooled until at the end of the first 3 minutes, it became cool enough for atomic nuclei to hold together. And then I made a wisecrack and I said that after that, nothing of any interest would happen in the history of the universe. And a friend of mine who was in the audience, another Harvard faculty member, Dan Bell, professor of sociology, heard that remark. He thought it was hilarious. And he got in touch with a friend of his, Erwin Glickus, the publisher of basic books. And Glickus got in touch with me and suggested I write this. I had never written a book before for the general public. I had only written this one highly mathematical treatise. So I said I would give it a try, and I did, and it worked.
So one of the things which was great about the first 3 minutes was that, well, first of all, many of us loved it. I couldn't remember why I loved it, so I read it again. And I find that the writing is extremely physical, that you have a way of thinking physically about physics. And for instance, I just wanted to give an example. When you updated in 1993 that book with an afterword, you said, quote, "In the 16 years since the first publication of the first 3 minutes, the universe has expanded by 1,300 billionths of a percent." And I read that and I just thought, I love this. It immediately brings to mind the picture of the expanding universe.
And no one is doing anything about it.
Yeah. So I realized that I then thought, oh my God, so the reason that I love your book is because you're a theoretical physicist, but you think physically like an experimentalist like me. So I thought of a Turing test we could do where in the Turing test, we don't check to see if you're a human or a computer. We check to see whether you're an experimentalist or a theorist. And I decided that you would definitely pass both theorist and experimentalist. So I'm just wondering, are you always that physical when you, sorry, not that, do you always think physically, sort of very down to earth when you're thinking about physics? Because a lot of your work is very, very mathematical.
Yeah, well, you know, as Feynman pointed out, I think in his Messenger lecture at Cornell, you have a terrible problem in writing for the general public without using mathematics, because our theories, especially when you get into things like quantum field theory, the Standard Model, are mathematical. It isn't just that we use mathematics to do calculations. The content of what we're constructing when we construct a theory is mathematical. So you have to struggle to explain things without the math. Cosmology is actually easier than particle physics in that sense because after all, the universe is pretty big, and you can describe the expansion of the universe in terms that are familiar in everyday life, like an expanding balloon surface. Everyone has an idea of what temperature is.
Well, I think a great theoretical physicist, which Steve certainly is, does both. Does the very abstract mathematical, and when you hear the physical explanations, the fact that he also understands it in complete mathematical detail gives it a kind of richness that it wouldn't have if it wasn't understood all the way from the top to the bottom.
I'm not a particularly strong mathematician, not as strong as Andy, I would say, just judging from his articles and mine. Most of my work isn't, well, all theoretical physicists are good mathematicians by the standards of everyday life, but there are some that are really good and others that just get along. I'm more in the class that gets along. I can learn this stuff when I have to. I once wrote a paper when I was just a new postdoc that used a very fancy theorem of set theory called the Heine-Burrell theorem, and I've never gone that far into pure mathematics in anything else I've done. That's more than half a century ago. The people like Andy who work on string theory now seem to me to be at a higher level of mathematical sophistication. But you, as Winston Churchill said, you just keep buggering on.
The other thing, which was I think that made the first 3 minutes really a classic and much loved, is that this idea you have that you don't want to condescend to the reader. Yeah. And in a huge amount of science writing, there's it's almost like the people are enunciating very carefully and yelling at you. And I wanted you to talk about this because you do it extremely well, and I'm wondering whether you also do it in teaching. Like, are you just not a person who condescends?
Oh, I certainly not aware of condescending. I'm always worried whether or not I'm getting across to students. I guess we all do. And I feel if I'm not, then it's my fault. I haven't explained it because it really is all explainable. I'm talking to, well, this year I've been teaching a course on quantum mechanics to graduate students. And they're certainly capable of understanding everything I'm covering. And if they don't understand it, it's my fault. I teach by Zoom. And of course, this past year, most of us have done that. And I like teaching by Zoom because I can put up the equations. I don't have to get up on the blackboard and make mistakes. It's all done in advance. Share screen, great thing. But what I don't get with Zoom is I don't usually get the feedback from the students, whether they're understanding it or not. I find that out when I look at the problem sets that they do. No, I don't see any reason to condescend. I don't think that people who aren't physicists are somehow mentally deficient for that reason. And most of my friends are not physicists, and I don't find any difference in intellectual level, but They know things I don't know.
So at the end of, since the first 3 minutes, the last afterword was in 1993, I was trying to figure out what has happened. And one thing that happened is that we measured that the universe was expanding, accelerating in its expansion, and that introduced dark energy and dark matter. You, in your book, The Third Thoughts, you have an essay in the Art of Discovery essay. You write, discovery in science depends indispensably on an interaction between theory and experiment. And in Uses of Astronomy, another piece, you write, the explanation of the dark energy is now the deepest problem facing elementary particle physics. So I wanted to ask both of you, actually, why is this problem so deep, and how might experiment help?
Andy?
Well, it's deep because we really have tried very hard and can't explain it. And it's particularly puzzling, or maybe I could explain what the problem is. You know, there's as Steve writes in the book, you can calculate how much dark energy there should be in the universe just generated by effects of the known particles in the standard models, electrons, muons, and so on. And they create a huge amount of dark energy, which we don't see. And so we have to cancel it by hand, and we have to cancel it. And following Steve, I won't use exponentials. We have to, he refuses to use exponentials in his book. We have to cancel it to 1 part in a trillion, 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 trillion. We really have to cancel it.
56 decimal places.
56 decimal places, right. And it's so weird, and there's no explanation for it. And what's particularly bothersome about it, I would say, is that we can't, it's something that happens at long distances. We're used to the idea that there are things that we don't understand at short distances. You know, for a long time, we didn't understand, you know, what the proton was made of. And eventually we got bigger and better accelerators, and we smashed them apart, and we looked at their innards, and we saw what they were made of, and we've been making bigger and bigger accelerators that tell us more and more about smaller and smaller things. But this is something that is happening at huge distance scales. And so no accelerators is going to help us. I don't know what the experiment is that's going to help us. In my mind, there was, you know, in my assessment of this problem, and people have very different views of it, there's really been only one interesting paper written, and that was both one of Steve's greatest papers, but surely his most annoying paper, in which before the tiny value of the cosmological constant was measured, he wrote a paper in which he said he used anthropic reasoning. And the basic idea of anthropic reasoning is that we can explain this small value of the cosmological constant because if it weren't so small, the universe would not have room for life. And Steve made this semi-quantitative. And then he made a prediction based on this anthropic principle that the cosmological constant would soon be discovered. And it was. Now, physicists hate this kind of reasoning because it puts us out of business. I understand that there was a time when the periodic table of elements was explained using the anthropic principle. If the
Well, I
elements were
didn't know
not,
that.
if the elements were not exactly what they take exactly the pattern that they do, we wouldn't be able to have life. Now, that didn't last very long because we got a much better, spectacular description of it. And so nobody bothers with that. So the anthropic principle, it puts us out of business, and it's very unsatisfying, and we'll never be sure if it's the right answer. And so but of course, the hallmark of good physical reasoning is that you can use it to make a prediction for an experiment which has not yet been done. It's very important that Steve said that before it was measured. If he'd said it after it was measured, we'd have all thought he cooked the books to make his reasoning match with experiment. But he said it before it was measured, and then it was measured. And so we might have to live with the anthropic principle, but I don't think we'll have another prediction coming from the anthropic principle.
Well, it's not a prediction, but there is an experimental test. If this is the explanation, you would expect the dark energy, that is the amount of energy per quart of space, to be constant. And on the other hand, maybe it's small because the universe is old and it's gradually getting smaller. We don't have any theory that looks like that, but you can at least talk about that. So it is possible to tell astronomically whether the dark energy is changing. And there are large programs of observation that aim at just this question. One of them is being carried out at the McDonald Observatory in West Texas, but there are others also, maybe even further along, to measure redshifts and redshifts, meaning velocities of things moving away from us, and distances of those things, of very large numbers of bodies, galaxies, or whatever. And this in principle can tell us whether the dark energy is changing. My guess, based on the anthropic business, is that it's not changing. If it is changing, I would say the anthropic idea is just as wrong. So this is falsifiable. But if it's not changing, it doesn't prove that it's right. I have to acknowledge that. Andy said that some people hate this. Well, David Gross, a very distinguished particle physicist, has said in so many words, I hate this idea. And I hate it too. I would much rather be able to calculate it rather than have fuzzy order of magnitude guesses based on anthropic reasoning. But there is one context in which anthropic reasoning is not only possible, but is inevitable, and that is what's called the multiverse. That is perhaps some picture like Andre Lindy's chaotic cosmology is correct, and the universe in very early times breaks up into separate expanding bubbles. And in most of them, the vacuum energy, the dark energy is large, positive or negative. They either wish out instantly or immediately recollapse. Every once in a while, one of these has a small, because of cancellations that Andy mentioned, has a small vacuum energy and it manages to expand. And some of them even expand long enough for life to arise. And naturally, any astronomer who studies the dark energy will be in one of those rare parts of the multiverse, because in all the other parts, there ain't anyone around.
But will we ever really know that Andre's theory or some other theory is correct? Wouldn't really nailing it, we weren't in
Well,
physics, we're not sure of things until we see them. We
I
didn't
would
really believe.
say, I don't quite agree with that. I mean, that's a kind of ultra positivist view. You know, from most of modern astronomy, we've been convinced that the moon is a sphere and that it has a backside which is completes the sphere. Nobody saw it. It fit our theories. And then we managed to get astronauts going around the moon, and sure enough, it is a sphere. You don't test things. I would say if a theory works, and it works in the sense that it's been very well tested in a lot of different contexts, you can believe it in other contexts.
Okay, yeah.
I believe quantum chromodynamics, which is the modern theory of strong forces, even though no experimentalist has ever seen a quark, because it makes predictions that work, including predictions that in certain kinds of collisions, you get sprays of particles that behave as if there's a quark inside. I think we might have a good theory of the early universe, which is tested in the way these theories get tested by looking at the inhomogeneities and the cosmic microwave background. And it may, for example, explain the mysterious fact that there's slightly more matter than antimatter in the early universe, which has survived to be the basis of what we, planets and stars and so on today. We may have a theory that makes successful predictions of all of these things. And if it also predicts a multiverse, I'll believe a multiverse. It doesn't, even though I will never see the other parts of the multiverse, I don't have to see everything, just like I didn't have to see the other side of the moon. You know, Andy, you gave a historical instance of anthropic reasoning, which turned out to be wrong. And that was the periodic table. But there's an older historic example, which turned out to be right. Galen, the Roman physician, explained the distance between the Earth and the sun, saying if they were much closer, the Earth would be too hot for life, and if they were much farther apart, then the Earth would be too cold for life. And that he had a vague idea of a benevolent creator, but in fact, that argument makes perfect sense because, as we now know, Galen didn't know, there are billions and billions of planets at all different distances from their parent stars. So naturally, on a small minority of them, the conditions are right for life. And naturally, any astronomer would be on one of those planets. I think that's a perfect analogy to the anthropic explanation of the dark energy, except we don't know that there are many, many expanding bubbles, like in Lindy's chaotic cosmology or some other theory of the multiverse.
I agree with you, like that seeing the other side of the moon is not necessary to believe that it's there in some circumstances. But the amount of precision that you would have to have about the laws of physics and the way before the first 1/100th of the second and the inflationary period in order to speak with confidence that the origin of the universe involved many bubbles. We're so far from that, from that kind of understanding of what really the structure of the universe is at that time and at that scales, that it seems to me not such an interesting discussion.
Well, one wouldn't want to spend one's life on it because
many people do.
As you suggested, progress is going to be slow, but I don't think it's it's
Yeah.
a hopeless task. And look what we've accomplished so far. I couldn't have dreamed when I was a graduate student that we would have a scenario for the expansion of the universe, the one that I described in this book.
It is incredible.
Which allowed you actually to calculate the abundance of helium and deuterium with which stars start their lives. And yet it works. And then not only that, we have a theory of an even earlier period, the theory initiated by Alan Guth at MIT, that the so-called inflation theory, which makes predictions about the distribution of inhomogeneities in the microwave background, and they also work, although I can't say that inflation is that well established, because conceivably other theories could, I mean, it isn't the kind of precise numerical prediction that convinces you the theory has to be right, but it certainly is a step in that direction. I talked, earlier I mentioned a wisecrack. The wisecrack I made was on a conference on the multiverse, which I've always been proud of this. This was a conference where we met in Trinity College, Cambridge, in the Master's Lodge, with a portrait of Isaac Newton looking down disapprovingly on us. And the discussion was the multiverse, and should we take seriously the multiverse? And Andre Lindy said he would bet his, he didn't say this at this meeting, but he had said it earlier, and I quoted him in a talk I was given. He had said that he would bet his life on the multiverse. And Martin Rees said he would bet the life of his dog. And I topped this. I said, to the extent that I believe in the multiverse, I would bet the lives of both Andre Lindy and Martin Rees's dog.
So
that's my favorite.
That's about where I stand on it too. I bet that.
So one of the things, Steve, that you wrote in Third Thoughts in an essay was about controversy, and how one of the things you actually enjoy was controversy about ideas. And so you write often about the history of science, and you with the statement that you're not a historian of science, but that you think you have something to offer, but that you like controversy. And I'm just wondering, that seems like, physicists like to argue with each other. And I'm wondering whether you started writing so that you could have more controversy in your life.
Sure. I mean, when you're writing something controversial and you get people upset, you know that you've reached them. You've had an effect. I've been involved. I get myself involved in a number of controversies. One is about manned spaceflight, which I think is an enormous waste of money. There are very good scientists who disagree with me about that. One of my professors at Princeton, John Wheeler, and I used to argue about that all the time. Other controversies are about the writing of history. I wrote a book about the history of science, well, actually the history of physical science, physics and astronomy mostly, called To Explain the World. And it got a terrible review in the Wall Street Journal by a professor of history at Harvard, who I won't name. And but he said this is an example of why physicists shouldn't write the history of physics. But I know what he meant by it. Historians are are always worried about being accused of what they call presentism, that is, judging the past by the standards of the present. And they have a very legitimate aim, which is to get back into the past. As the German historian Ranke said, wie es eigentlich gewesen, how it really was. And if, for instance, if they want to write about Einstein, they would go back into the patent office and his worrying about railroad trains, exchanging light signals and so on. They would get into Einstein's framework. They wouldn't worry about the way we think about relativity today. But there's another, and that's a valid aim, but there's another aim, which is to study not just the science of one time, but the development of science, the progression of science. And of course, that makes only sense if you believe that science does progress, which I do believe, and most of us believe. But there are people who treat science as like a change of fashion. You know, every 50 or 100 years is a new fashion and people do a new kind of science. I don't think that's right at all. That's associated particularly with the name of Thomas Kuhn. So I get into that controversy also. And I've been involved in controversies about the ballistic missile defense. That goes way back in my life. I long before I wrote the first 3 minutes or Gravitation and Cosmology, I was involved in a book attacking the Nixon Sentinel ABM system that was written under the auspices of Senator Edward Kennedy, with Harvard people, Abe Chase in particular. But I do enjoy this sort of thing. I mean, you know, you're alive. This is a way of knowing you're alive.
The other thing you wrote about, and I was interested in both of your responses to this, is on being wrong, is a little essay. And you talk about one example when you were 23 and parity violation, when it was discovered, or when it was proposed that the world was not symmetric when you looked in a mirror. And you said that's obviously got to be wrong, and then it was proven right. Are there other examples that you can think of where you were wrong?
Oh, probably, if I think about it. I'm not wrong that often, not that badly wrong anyway. The point of raising that, by the way, was not to show how dumb I am, but to point out that it's a wonderful thing about science that our standards of verification are sufficiently good so that we can realize that we have been wrong. I mean, how often does an economist announce that they've been wrong about something? That occasionally does happen. How often does a religious leader announce that they have been wrong about something? I don't recall that happening, not in modern times. But we in the sciences are forced often to recognize that we've been wrong, and that's a very cleansing experience. That was the point of the talk I was giving to a graduating class at Rensselaer Polytechnic. Where have I been wrong otherwise? I remember a case where I was wrong, sort of silly. There was a problem of there's a particle called the pion that decays mostly into another particle called a muon, which is a little lighter. And the muon is like a heavy electron. And for some reason, the pion doesn't often decay into an electron, overwhelmingly likely to decay into a muon and not an electron. Well, at the time that this was an issue in the 1950s, there were two possible theories of the decay process. For the physicists present, I'm talking about axial vector and pseudoscalar coupling. In one picture, um, the electron to muon ratio would be non-zero, but quite small. And in the other picture, it would be quite large. I thought at that time, experiments showed that not only was the ratio small, it was even smaller than the theory that predicted it would be small. In other words, it was so small, they weren't seeing it at all, and no theory accounted for that. So I assumed that it had to be zero, that pions never decay into electrons. And I made a bet with a professor at Columbia, where I was a postdoc, Norman Kroll, that a dollar bet that the pion would never be seen to decay into an electron. And then about a year later, it was found that it did decay into an electron at just the rate that you would expect from one of those two theories. The experiment had been wrong. I was wrong in believing the experiment. And this is a mistake I've made several times, taking experiments too seriously. Pardon me, Melissa. Andy doesn't mind hearing this. He's a theorist, but Melissa's an experimenter. But I wasted a lot of my time trying to understand theoretically experimental results where the results just turned out to be wrong. And I won't go through the whole list. There's a saying ascribed to Arthur Eddington, a British astrophysicist, that you should never believe any experimental result until it's confirmed by theory.
So
Well,
I just have, yeah, just to either of you, supersymmetry is something which we've never seen, and it seems like everybody believes it must be there. Is this one of the cases where you?
I don't believe it must be there. I think it's a very attractive possibility. We have this problem called the hierarchy problem, that there's a huge gap between the scale of the standard model particles, the proton and the quarks and all that, and the scale at which gravity becomes effectively a strong interaction. There's about 18 powers of 10 in between these scales. And I don't know any rational way of explaining where this hierarchy comes from, except in terms of supersymmetry. But as you say, Melissa, there's no sign of supersymmetry experimentally. It may turn up if we can convince the public to pay for the next generation of accelerators. It might have turned up if Congress had not canceled the superconducting super collider in Texas, which would have had 3 times the energy of the CERN Large Hadron Collider. It might have turned up already. It's certain, I don't really classify things like this as right or wrong. Who knows whether it's right or wrong, but I do classify it as worthy of being taken seriously. And I wrote a book about it. So that shows how serious I was.
Okay.
No, go ahead.
No, Andy, do you have I soon I have to go to the audience because it now is
Well, I think I have a much more intimate experience with being wrong than Steve. I'd say starting in college, I believed in a theory, Marxism. Experiments were done. Seems to be wrong. And I believe, and then afterwards, and a lot of, I haven't been wrong in the sense of, I haven't published papers with errors in them. There might be a few factors of 2 in some of my papers, but, I've guessed about what directions that might be interesting, and I've often been wrong, and very often been wrong. And also I, as a graduate student, I made a guess that the problem, the deepest, most interesting problem that I could hope in physics that I could hope would be solved in my, or great progress be made on in my lifetime, was the problem of reconciling quantum mechanics with Einstein's theory of general relativity, and moreover that black holes where they meet was the place where that would be the engine that would drive our progress and understanding in that. And I've put my life's work on the line on that guess that that was an interesting thing to do. I could be wrong, it could have been the wrong guess. It could be, it doesn't feel that way. Of course, I get more excited every day by what we're doing, but we haven't, brought the, whatever the phrase is, brought the cows home like Steve did with the standard model, we could all be on a wild, wrong adventure, so it's there's a lot of I think to do really creative physics, and it must have felt to you like this at an earlier stage. You have to risk being wrong, and if you're not going to risk being wrong, you won't get anywhere.
Andy points out that the real danger is not just being wrong about a factor of 2 or something, but being wrong programmatically, working on working in a direction that doesn't really lead to much. I've done that a lot. I have. There was a time I wrote about a dozen papers on something called the Quasi-Particle Method, which was an attempt to deal with the strong interactions by introducing bound states like the proton as if they were elementary into a quantum field theory, and it never went anywhere. It was a waste of time. I learned some mathematics, but it's something that's well forgotten and has been forgotten. And I've done a number of those things where the being wrong was following the wrong lead, but you have to keep trying. I make in one of the essays in this book, Third Thoughts, I compare the work of a theoretical physicist with the work of an artist who is free to put paint on canvas or words on a page in composing a poem any way he or she likes, but most of them don't work. Most of them don't produce anything worthy of saving. Every once in a while, you do something that works. And I think in that sense, this is an essay in here called The Craft of Science and the Craft of Art.
Yes.
That, and that is, I think, for both artists and scientists, a crucial necessity. You have to be willing to waste time pursuing false leads.
So I have
art wasting time in the right way.
Well, sometimes it isn't the right way.
Yeah.
So I have a few questions from the audience, mostly anonymous. One person says, I absolutely love this line you wrote in the epilogue to the first 3 minutes. Quote, the effort to understand the universe is one of the very few things which lifts human life a little above the level of farce and gives it some of the grace of tragedy. Have the years since you wrote it changed your view, and do you still believe it?
Oh, I believe it. I did. That wasn't the last line, though. No, that's right. That was the last line. But there are other things. I said it's one of the few things, but maybe I should have emphasized more that there are other things like loving people and enjoying beauty. But with the fact that our condition is tragic, I haven't changed my view. We're all facing our own extinction and the death of the people we love. And I don't believe that there's anything that's going to follow that. I think it's every one of us is in the middle of a tragedy in that sense. And we have to do our best in this. As Yeats says, if worthy our part in the play, we have to be worthy of it. Even though it's, in the end, it's all nothing.
So another person asks, does Professor Weinberg think string theory is a productive direction for fundamental explanation of the universe, i.e. is Professor Strominger's work yielding useful insights? I think this person also likes controversy.
Well, I think it's yielding very useful insights, and I think it's been disappointing because the idea of string theory as a theory of fundamental forces has been around now for quite a while, a number of decades, and it has not led to the kind of specific prediction. Well, it makes some qualitative predictions, like it explains why gravity has to exist, but it has not led to the kind of specific numerical predictions which will say, well, okay, now you can take it to the bank. But it's the only game in town. There are alternatives for pictures of what happens at very short distances. There's one due to me called asymptotic safety, which I think is a possibility worth taking seriously, but is much less attractive than string theory. And I hope string theory is right, and I don't see anything else on the horizon that's remotely as attractive. Andy, do you agree with that?
Well, I could comment on that. So there's Steve, you are certainly the most eloquent champion of the reductionist program in physics, that progress in physics is understanding things at shorter and shorter distances. And there was a moment in the 80s where it looked as if string theory could be the final step in that reductionist program. That moment evaporated very quickly within a year or two, I would say. And instead of being everything, it is more, it's a wellspring of ideas. It gives us ideas of how different quantum systems fit together. And it could find a place in nature which isn't exactly the final capstone on the reductionist program. And the example I would like to use to put this in perspective is Yang-Mills theory. Yang and Mills invented Yang-Mills theory to explain the relationship between the proton and the neutron. That was wrong. I've never heard anybody say Yang-Mills theory is wrong, but what Yang and Mills wanted to do with it in that 1954 paper was undeniably wrong. It doesn't explain. Now, it doesn't explain that. It explains something else. And you got your Nobel Prize, and other people got them too, for understanding what it was that it did explain. So we wouldn't say Yang-Mills theory, certainly Yang and Mills didn't understand how Yang-Mills theory fits into nature. And I think string theory is like that. It has an inevitability to it like Yang-Mills theory did. Maybe it's not ruled out that it is the final endpoint of the reductionist program, but it might find a place in nature. And that's how it feels to me, that it has and that's already happened to some extent. We've used it to explain things about superconductors and heavy ion collisions and so on. It might find a place in nature that isn't exactly what its originators imagined. And it almost never happens in physics that an idea comes out fully formed into its right place. They get battered around, and that I think has already happened to a great extent with string theory. And then it's not right in my mind to hold it up to the standard of it should be a theory of everything or it's not interesting.
Oh, I agree with that. But I still have hopes that there will be a final theory that in just the way you describe what happened to the Yang-Mills theory and how it was built into the standard model in a different form, that string theory maybe in some different form will appear as an ingredient in a final theory. We don't know. I mean, in a way, your Yang-Mills example also counsels patience, because when the Yang-Mills theory was first suggested, Pauli thought it was nonsense because it predicted that there would be massless particles that
Right.
were clearly not seen experimentally. Right. And it took a long time to understand why we don't see those massless particles.
So we have one more question. I mean, we have way more, but we have one more question that I just want to ask before the time is up. Maybe we can do this. The person says, I wonder if we can get a question in about the philosophy of quantum mechanics at the fundamental level, in particular, how important you guys, believe resolving the interpretations, particularly with respect to observation a la Bohr versus Everett is. Is it a distraction or a fundamental question that needs to get resolved so we can make fundamental advances?
Oh dear, that's a controversy there. I think it's an important issue. I'm not happy with either the Bohr or the Everett. Those are just names that go for a large body of interpretive wisdom about quantum mechanics. I call it realist and instrumentalist approaches to quantum mechanics. I'm not happy with either. There are people who are perfectly happy.
I'm one of them.
You're one of them. It doesn't matter when you do any work, whether it's the standard model or black holes, anything. You don't really have to worry about these deep issues. But at the same time, I do worry about them. What I worry about is not what worried Einstein, the spooky action at a distance. That we just have to live with. And it doesn't violate relativity. What worries me about quantum mechanics is the fact that it puts its principles, its underlying postulates refer to observers. And I would expect that the existence of observers is something you learn about as an end of a long train of deduction from fundamental principles. You don't put in the laws of nature themselves that there are beings that somehow can make observations. And I think Everett felt that way, and he was trying to resolve that problem with his many worlds interpretation, which I think is also no good for different reasons. So I'm unhappy about the present state of quantum mechanics, which doesn't prevent me from using it. In fact, what else would you do? You can't live without using quantum mechanics. So that's the position we're in. I do think that Einstein himself, I think, was terribly wrong talking about being wrong, not only in pointing out disturbing things about quantum mechanics, but then turning away from it and refusing to use it in his own work, which went nowhere after this time in the mid-1930s.
The thing I love about physics is in almost no other sphere of life is that there's right and there's wrong, and we eventually get to know, is this theory right? We do experiment, eventually we get there. It may take a long time, but we get there. And my view, if you can do a calculation and it predicts the outcome of an experiment, that you understand it, as long as you can do the calculation. So nobody ever stopped if they were trying to compute, what happens when you collide protons and what comes out. Nobody ever said, wait, at this point in the calculation, do I use the Copenhagen interpretation or the Everett interpretation? Everybody agrees on what the calculation is that should be done. They disagree on what the words you use, what words you should use to describe the calculation you're doing. But that, I think, is no longer physics. We're all allowed to think about it however we wish, but we all agree on what calculation should be done. And if, quantum mechanics has been tested in the anomalous magnetic moment of the muon to whatever it is, 16 decimal places, we understand it. If we can compute it to 16 decimal places, I think we understand it.
Well, that's
But like
exciting.
you, at night, I think about these things and wonder about them. But yeah,
Soon we should hear about this muon. There's data coming. The G-2 of the muon is next week. So this was really nice. I have way more questions, Steve, for you, but our time is up. And I want to thank you a lot for having this conversation. And I think Kate will be coming back. Yeah.
Hi, yeah, I just have some closing words. So unless you guys have anything else to wrap up, I can take us
I
out.
just wanted to say that I enjoyed the evening with Melissa and Andy. And
I enjoyed too. Yes,
it was a lot of
pleasure to
fun.
see you.
And a frank exchange of views.
I've been learning from Steve since I took general relativity as an undergraduate.
I
And it
see.
continues.
Where was that?
When was that?
Where?
Harvard. You taught
Oh.
there.
I see. I didn't understand what you meant. I see. I
Yeah,
forgot that. Uh-huh. Well, it's a pretty good university.
It's okay.
Well, thank you tremendously, Steve, Andy, and Melissa, for this fascinating discussion and all of your viewpoints. And thank you everyone out there at home for joining us tonight. If you would like to learn more, copies of the books are for sale on harvard.com. I've been putting some links in the Zoom chat. But on behalf of Harvard Bookstore, the Harvard Division of Science, and the Harvard Library, have a good night. Keep reading and keep learning, and please be well. Thank you, everyone.
Bye.